Example 5.5, the platform diver. We want to use conservation of energy to calculate the speed of a body falling straight down in the presence of gravity. They're using conservation of energy in the form kinetic energy initial plus kinetic potential energy initial equals kinetic energy plus potential energy final. You can use that if you want. I am actually gonna try change in kinetic energy equals negative change in potential energy. I think that's how it works, right? Your potential energy goes up as your kinetic energy goes down, and that's also equal to the work. Work equals your kinetic energy goes up as your potential energy goes down, and the work done by the field is equal to the change in kinetic energy, or by the potential force, whatever the force is that's causing the potential energy. All right, so this diver, he's diving from 10 meters to 5 meters. We want to find out his velocity at this point, and then he hits the water, and we want to find out his velocity at that point. So his change in kinetic energy would be kinetic energy final, which is going to be 1/2 mv final squared, minus his kinetic energy initial, which is minus 0, because he starts up at the top of the platform at 0. The change in potential energy is going to be just going to be mass times gravity times the height that he's traveled. So that's how it's either going to be 5 or 10 meters that he's traveled. So this is our basic equation, and we can cancel out our m's because that appears on both sides of our equation. We'll have v final squared, multiply both sides by 2, we'll have 2gh, take the square root, and we'll have v final equals square root of 2gh. And so for part A, we'll have v final is square root of 2 times 9.8 times 5. And for part B, we'll have v final equals square root of 2 times 9.8 times 10, which come out to be 9.90 meters per second and 14.0 meters per second. Question 5.5. Qualitatively, how will the answer change if the diver takes a running dive off the end of the board? Well, that is going to modify this term here, because right here we have the change in kinetic energy is 1/2 mv final squared minus 0. This would be minus 1/2 mv initial squared. So I would end up putting plus 1/2 mv initial squared over here, and dividing out the m, we would have, and multiplying by 2, I would have plus v sub naught squared there, and plus v sub naught squared there. So our answer would be affected by having a number well over the v sub naught squared, or qualitatively, the final velocity would be more than it would have been if he hadn't taken a running leap. So we can work it out. 3.5 meters per second, they tell us. So when he strikes the water, we'll use this equation here and get square root of 2 times 9.8 times our height is 10 plus 3.5 squared. We'll see if we get the right answer. Yes, I got 14.43, which rounds to 14.4 meters per second. Cool. we got the right answer. Let's see if 5.6 is just as easy. Problem. A powerful grasshopper launches itself at an angle of 45 degrees above the horizontal and rises to a maximum height of 1 meter during the leap. With what speed did it leave the ground? Okay. This is kind of weird because as the grasshopper jumps, he starts to lose energy, and he loses all of his kinetic energy in the y direction, but he doesn't lose any of his kinetic energy in the x direction. So his change in kinetic energy is just associated with his velocity in the y direction, which would be velocity of y will be v times the sine of 45 degrees that he leapt up at. So his change in kinetic energy is going to be associated with that v sub y, 1/2 m v sine theta squared, and his change in gravitational potential energy is just going to be mg times that 1 meter, so h. Okay, so now we can cancel out some things because the m is not going to matter. And then we want to solve that for v. So we'll take 2gh over sine squared of theta equals v squared. And so v will be equal to square root of 2gh over sine theta. And that comes out to 6.26 meters per second. Question 5.6. For all other given quantities remaining the same, how would the answer change if the initial angle were smaller? So visualizing that, we would have to picture the grasshopper jumping from here at a smaller angle and coming up to the same height and going back down again. New theta. We are dividing by a smaller number, so that means the initial velocity must have been larger to get up to the same height with a smaller angle. In exercise 5.6, catapult launches a rocket 30-degree angle with respect to the horizontal and find the maximum height attained if the speed of the rock at its highest point is 30 meters per second. So they tell us that its velocity when it reaches the peak is 30 meters per second. So that means that the velocity purely in the x direction must be 30 meters per second. It's launched at an angle of 30 degrees, so I can use the tangent equation, tangent 30 equals v sub y over v sub x. And we would have v sub x tangent of 30 equals v sub y, or 30 tangent 30. So v in the y direction must have been 17.3. At this point, I can apply the equation that mgh is equal to 1/2 mvy squared, cancel out my m's, and solve for h equals v sub y squared over g, or 2g rather, and you get 17.3 squared over 2 times 9.8 equals 15.3 meters. So I think the key takeaway from this problem is that we can make a little bit of a modification to this equation 5.15 and add an extra 1/2 mv sub x initial squared plus 1/2 mvy initial squared, and it will be still a good equation. So I had earlier mentioned that kinetic energy could be split into linear kinetic energy and rotational kinetic energy, but now we realize the linear kinetic energy can be split into v sub x, v sub y, and v sub z. And since v sub y squared, or like v squared is v sub y squared plus v sub x squared plus v sub z squared, you can split those out without any loss of generality. Or actually, I guess you're gaining generality. There's a warning here, a tip: don't use work done by the force of gravity and gravitational potential energy. I kind of covered that a little bit earlier by saying that the work done by the gravitational potential energy is equal to the change in kinetic energy is equal to the negative change in the potential energy. So if you're including the terms of negative change in potential energy, you're already actually including the work done by the field. So